Hey folks, in this video we'll talk about an important rule and tool called L'Hopital's rule. So this will help us take limits that previously we couldn't do. So we'll use derivatives to take some of these limits. To motivate this, let's consider this limit cosine x over 2x minus pi as x goes to pi over 2. So you can check, if we just go ahead and try to plug in x equals pi over 2, it doesn't work. We get 0 in the denominator, but also 0 in the numerator. So 0 in the denominator implies maybe that this thing should be approaching infinity, but a 0 in the numerator implies that it should be maybe approaching 0. We've got these kind of conflicting forces. It's not clear what the answer is. So we'll go back to a handy idea, the idea of a linear approximation or a tangent line. Cosine x is not a line, it's a curve, but any function very close to a point behaves pretty close to its tangent line. Excuse me, any differentiable function does that, and cosine of x is differentiable. So you should check that the equation for the tangent line near pi over 2 is minus 1 times this quantity, x minus pi over 2. And if we sort of leverage this fact that cosine x behaves like that line, we can replace it in the expression. The denominator, we can factor a 2 out here, and then we get a term that cancels. And once we cancel the term, we can see easily this limit is minus 1/2. So the idea of using the tangent line approximation, or really the slope of the tangent line, pays off here. And that's what's at work when we use something known as L'Hopital's rule. So L'Hopital's rule helps us to deal with limits that are ratios. So if we've got a limit that looks like f of x over g of x of a particular form, then we can use L'Hopital's rule. And that form is, if it looks like, and I put this in quotes because, well, it's kind of what we would have if we just plugged in the value. If it looks like 0 over 0, or infinity over infinity, and I don't really care about the signs of the infinities, then L'Hopital's rule tells us what we can do is take the derivative of the top function, the derivative of the bottom function, and take the limit of that expression. Now this is something we would never do usually. We've got a quotient rule that tells us how to take a derivative of a quotient or a ratio, and this is not the quotient rule. But when we're taking a limit and we've got an expression that looks like one of these forms, which we'll call indeterminate forms, then L'Hopital's rule lets us hopefully take an easier limit. So let's try some examples. In this first example, you can check if we plug in x equals 0, upstairs and downstairs, both give us 0. So this thing looks like 0 over 0 as we approach x equals 0. We can go ahead and apply L'Hopital's rule by taking individually the derivative of the top, the derivative of the bottom of this fraction, and then we get something that's easy enough. We can just go ahead and plug in x equals 0 and get 4. The next example, you can check, well, we can't exactly plug in x equals infinity, but we know that, well, as x gets really large, x cubed gets really large. As x gets really large, e to the 2x gets really large. So these things approach infinity. Well, infinity over infinity, that's an indeterminate form. So we're clear to use L'Hopital's rule in that case. And we'll take the derivative upstairs and downstairs, and say that our original limit now is equivalent to this new limit. Unfortunately, it's not much easier. We still get infinity over infinity or something that looks like that. So what we'll do is actually apply L'Hopital's rule 2 more times. You can check at the next step. Again, we have an indeterminate form. And while the limit's not any easier to take, it's getting a little better each time. So finally, we get something 6 over e to the 2x times 8. We can plug in x equals infinity. Well, we can't plug it in. We can let x tend to infinity. When that happens, we've got a constant number upstairs. The bottom is getting really large, so this quantity is approaching 0. And now the last example looks a little bit out of place here. This is not a ratio. So, well, let's look at what we've got. We want x to go to 0 from the right, and that's important because ln doesn't have 0 or any negative numbers in its domain. But if x is getting close to 0 from the right, we can talk about the values of natural log. Well, of course, as x goes to 0, the value of x approaches 0. The value of natural log of x, if you look at the graph, actually approaches minus infinity. So we've got something very small times something very large, well, negative but very large, and we've got these sort of competing forces. Although this is not an indeterminate form for which we can apply L'Hopital's rule because it's not a ratio. So what we'll do is we'll take this expression and rewrite it, sort of force a ratio. And we'll do this using exponents. X in the numerator is the same as 1 over x, or x to the minus 1, in the denominator. So if I write that, ln of x over 1 over x, we can check the numerator is going to minus infinity. Well, we recognized that before. And 1 over x, as x gets close to 0, goes off to infinity. So now this is an indeterminate form. We can apply L'Hopital's rule to get a new limit. Take the derivative upstairs, downstairs. And we get this. It's not clear that that's better, but if you simplify, we see that this is just equal to minus x. And the limit as x goes to 0 of minus x, 0. So what does it tell us about these competing forces? X that's getting small and natural log of x that's getting really big in the negative direction. This tells us that the x sort of wins out, that it's getting close to 0 faster than the natural log is growing. So this is a L'Hopital's rule in action. We'll see some more examples in class.